Hello guys, in this video I am going to solve this question number 2 from this chapter 8 from the book Engineering Circuit Analysis by Hayt, Kemmerly and Derwin. So the question says that it is given that the current is equals to 1 at t equals to 0. So at t equals to 0, current is equals to 1 ampere. It is also given that R, it is 100 ohms. And we need to determine, it is given that select L such that I is equals to 360 milliampere at 50 milliseconds. So it is given that at t equals to 50 milliseconds means 0.05 seconds. So at this I is equals to 368 milliamperes or 0.368 amperes. And with this data we need to determine the L. Now for this type of a circuit where we have a R and L only, so for this type of a circuit we know that this current IT, it is defined as IT is equals to I naught e power minus R by L t, right? Now if this I naught, it is the initial current, means the current at t equals to 0, and it is given in the question that this is equals to 1 ampere. At t equals to 0, current is 1 ampere. So simply we are going to substitute this I naught as 1 ampere. So means simply I can remove it. Now coming to this part, over here it only we know is the R. So R is 100. So simply I can write it as 100 by L t IT. Now we know that at t equals to 0.05 seconds, current is 368 amperes. So substituting this value 0.368 equals to e power minus 100 divided by L, and the t is 0.05. It means it is 0.368 equals to e power minus 5 upon L. Taking the natural logarithmic on both sides, we get this. Now this, if you solve it in a calculator, this is approximately equals to -1. So from this we will get the value of L as 5 Henry. So this is the answer to the first part of the question where we need to determine the value of L. Now the second part of the question says that we need to compute the energy stored at the inductor at t equals to 0, 50 milliseconds, 100 milliseconds and 150 milliseconds. Now we know that the stored energy within the conductor, it is given as half L I square. I is the current flowing through the inductor, right? So over here, like, let me create one table. So over here, let me create one table. T I L, right? Now for we need to calculate the energy at t equals to 0 seconds, 50 milliseconds, 100 milliseconds and 150. So 0, 50, it is milliseconds, right? So 50, 100, 150, right? Now I, if we look at the I, the formula, like, since our L is 5, so substituting this value of the value of L in this equation, what we are going to get? We are going to get our IT will be equals to e power minus 100 by 5 into t, right? It means that IT will be equals to e power minus 20t. So this is our current that is flowing through the inductor, right? And this is the formula to determine the energy. So not L, it is WL, half L I square. Now for t equals to 0, simply we can determine the current by substituting this t equals to 0 in this. So if I substitute this, so simply I will get e power minus 20 into 0, so it will be 1 ampere, right? It will be 1 ampere. So at t equals to 0, you can see it is also given in the question, right? So it proves that our equation is correct. So at t equals to 0, current is 1 ampere, and now substituting this 1 ampere in this equation, we will get WL is equals to half into 5 into 1 square. So it is 2.5 joules, right? Now similarly, if we substitute the value of this is 50, right? And this 50 is in milliseconds, so we need to convert it into seconds, so it is 0.05 seconds. So substituting this value over here, so we will get current as e power minus 20 into 0.05, right? And now substitute solving this, you will get it is as 0.135 amperes, and substituting this value of I in this equation, you will get W is equals to 0.339 joules. Now similarly for this one, this 100, it is 100 millisecond, it means 0.1 second, right? So if you substitute this value in this current expression, in this expression, so we will get e power minus 20 into 0.1. Solving this, you will get the current value as 0.018 amperes, right? And WL, substituting this value of current in this equation, you will get WL as 0.046 joules. And last, this 150 millisecond, it is 0.15 seconds, right? And substituting this value over here, you will get 0.0024 amperes, right? And WL, it will be 0.006 joules. Now over here with this, so this is the answer to the second part of the question, where it is asking that we need to compute the energy stored in the inductor, right? Now we get the answer. Now if you look at the answer, from this answer you can also verify if we are getting the correct answer or not. How? Because like as you can see in the circuit, there is no battery, and since there is no battery, so whatever is the energy that is stored in this inductor, that energy will be consumed, will be dissipated through the resistor. It means that the energy that is there within the inductor, it is going to decay with time, and at the end it will become zero, right? Similarly, the current that is flowing through this inductor, it is also going to decay with time, right? And it is the reason we get this type of the formula. And the same thing is reflected by this table. You can see at t equals to 0, current is 1. Current reduces to this after 50 milliseconds. Current decays further at 100 milliseconds, and it decreases further. It becomes 0.024. It reduces more at 150. So as the time is increasing, our current, it is decreasing, right? And if you look at the energy, this is the energy of the inductor, which is going to decay. Which is going to decay due to the energy dissipated through the resistor, right? So this energy is going to decay. So you can see that with time this energy is also decaying. Initially it was 2.5, then 0.339, then 0.046, and then 0.006. So with this, since the energy is also decreasing, current is also decreasing through the inductor, so it further proves that the solution is correct. So if you have any doubt, you can put it in a comment box, and do subscribe my channel and share this video with your friends and colleagues. Thank you.